In this video, we will define some of the different entities in the ladder height setup and also write up a few identities, formulas, truths, if you will, that are useful if you're working with ladder heights and things in general. So this is for those of you who kind of want a set of formulas to work with. Let us first start out by defining three things that are quite important to define. One is ladder time. One is ladder height. And the last one will be inter ladder height time. Now, the ladder time, you can see, is defined as what we spoke about in the previous video, but if we want to write it up formally, then there is a way we can write it up, and it is given as, first of all, that the first ladder time is equal to 0, and then the ith ladder time is given as the first time point where the first time point after the previous ladder time, where it holds that x at that time point is strictly smaller than x was at the previous ladder time. Now note that these ladder times might not necessarily be finite. They may actually be infinite. And the case where they are infinite occurs if, for example, we look here, the first, second, and third ladder time is well defined and finite. However, if this process just goes up and up and up and up and never comes down here again, then the fourth ladder time will be infinite. Now to ladder height. Ladder height is well defined if the ladder time is well defined. So we have to write here, if ti minus is indeed smaller than infinity, then the ladder height is well defined, and the ith ladder height is given by the difference of x at the ith ladder time and x at the previous ladder time. And if the ith ladder time is infinite, then the ith ladder height will never be observed. Two things that are quite useful to note is that, let's see, two things that can be useful to note here, or at least one thing that is useful to note, is that the ladder heights are IID. So note, let's just write it here. Note, if the ladder heights are well defined, then they are IID. Okay, so let's continue to the inter-ladder height time. The inter-ladder height time is the time that elapses from one ladder time occurs to the next ladder time. So the first inter-ladder height time that we have in this example here, tau 1 minus, is the time that goes from here to here. And the second inter-ladder height time, tau 2 minus, is what we have here. And the third inter-ladder height time will be what we have here. And here we can see quite clearly that the definition of the ith ladder height time, so Ti tau I minus, is given as the difference between the ith ladder time and the I minus first ladder time. One thing that is quite useful to note is, due to the strong Markov probability of the Cramér-Lundberg process, the inter-ladder height times are in fact identically and independently distributed. And also, since each time this process restarts, then the inter-ladder height time is also the amount of time that elapses before this new process here goes below its initial value. So the inter-ladder height time is in fact also the same as the amount of time it takes for a Cramér-Lundberg process starting in 0 to achieve ruin. And therefore, the probability that this inter-ladder height time is finite is also equal to the probability that ruin will occur in this Cramér-Lundberg process if the initial capital had been 0. So we now have the ladder time, the ladder height, and the inter-ladder height time. One thing that you may note is that in the exercises, sometimes they call the ladder time. They sometimes call the ladder time the ladder epoch. So that may be useful to just remember. Okay, now we will also define one more thing, which is K, the number of observed ladder heights. So let's just write here. Let K be the number of observed ladder heights. In the exercise, they actually write K up in a specific way, which we will also do here just for fun. They say that K is equal to 0 if the first ladder time never occurs, if the first ladder time is infinite, and otherwise K is equal to the greatest I for which the ith ladder time is observed. I may be paraphrasing the definition here, but that is what is in the exercise. What you can note here is that K is a stochastic variable that depends on the ladder times. So if you want to say something about the distribution of K, you will have to say something about the distribution of the ladder times. Now, one more thing, which is also a useful observation, a useful note, is this. If the ladder heights are well defined, then the ladder height process is independent of K. That will be useful later. So all of these that we've written up here are useful formulas, and just before we continue, there is one more formula that is useful that I would recommend that you write down, and that is a result from lecture and also from the lecture notes that tells us about the distribution of the ladder height. Which says that the probability that a ladder height exceeds x is given as 1 divided by the mean value of the claim size multiplied by the integral from x to infinity of 1 minus the distribution function of the claim size. And I think that we don't have more formulas for this ladder height setup. Well, this is also more than enough for you guys to use. Those of you who have attended lecture probably don't need this because you already have it in your own notes. But those of you who haven't attended lecture might find this useful. See you in the next exercises where we start solving.